So we're going to start today by talking about something called mass defect and binding energy. So here's where I'm going to start. A proton has a mass of blah, a neutron has a mass of blah, and an electron has a mass of less blah. Determine the mass of magnesium-24. Well, magnesium-24, we know we have 12 protons, 12 neutrons, and 12 electrons. So, if I take 12 times the mass of the proton plus 12 times the mass of the neutron plus 12 times the mass of the electron, and I add those things together, what I get is 24.1978752 U. Great. The problem is, if I look up the mass of magnesium-24, what I get is 23.985,042 U. Well, that's weird. So if I subtract those, what I get is this, 0.2128332 U. Okay, so that's interesting. Okay, the mass of this nuclide, this isotope, is actually less than the mass of all of the individual pieces together. All right, which means that mass has been lost, and that's weird. But because we're talking about things that are really small, what actually ends up happening is that this mass gets converted to energy using the equation E equals mc squared. Okay, that mass gets converted to an energy. All right, and we call that energy binding energy. And if we think about it, that binding energy is going to tell us about the stability of the isotope, because the higher the binding energy, the more energy that you lose when when all of these pieces come together, the more stable the nucleus is going to be, because you'd have to put that energy back in order to break apart these isotopes. So I can also take this binding energy and divide it by the number of protons and neutrons in the nucleus, and I get a kind of stability per nucleon. Okay, stability per proton and neutron. And like we like to do, I can take that binding energy per nucleon and graph it versus the mass number. And when I do that, I get this table. Okay, now let's talk about what this means. All right, so the thing with the highest binding energy per nucleon, which means it's the most stable, is iron. Okay, great, awesome, wonderful. And so what ends up happening is that a lot of things will tend to form iron. Iron is very, very stable. And so what happens if something has a high binding energy per nucleon? Or, sorry, a lower binding energy per nucleon? Well, it means that it becomes unstable. And what's interesting is that if you take the number of neutrons and you divide them by the number of protons, and then you graph them for all the stable isotopes of all the elements, they form this little band here. And we call this the band of stability. And it is between a neutron to proton ratio of 1.5 to 1 to 1 to 1. So you need more neutrons in there to balance the fact that the protons want to repel each other. So the neutrons provide the strong nuclear force that holds the nucleus of an isotope together. And so what you can do is you can take all of the isotopes, all of the possible isotopes, and you can graph them. And some of them are going to be stable, and that is these black ones right here, okay? Those isotopes are stable. All of the other isotopes are not stable. And when they're not stable, they tend to fall apart, and we get nuclear decay. And we're going to talk more about that in a minute. But before we do that, we need to talk about balancing nuclear reactions. Okay, and the important thing to keep in mind here is that we have to follow the law of conservation of mass, meaning mass cannot be created or destroyed. Now, I know I just said that binding energy seems to violate conservation of mass, but it kind of doesn't, because that mass gets converted to energy. All right, here we're looking at a straight up conservation of mass. So when we talk about conservation of mass, we're talking about the fact that the mass number must be the same all the way through, okay? So we can't like destroy a proton or a neutron. So what that's gonna mean when we're balancing these nuclear reactions is that the sum of the mass number on the left side of the equation has to equal the sum of the mass number on the right side. So in this case, I have a total mass number of 14 on the left side, right? Mass number of 14 on the left side. And then I have a mass number of 14 plus 0 on the product side. That's going to work out. All right, the other thing that we have to be careful of is conservation of charge, okay? So with the conservation of charge, what we're talking about here is the sum of the atomic number on the left has to be equal to the sum of the atomic number on the right. So here on the left side, I have an atomic number of 6. And on the right side, I have -1 plus 7, and that equals 6. So that is also okay. So when we're balancing nuclear reactions, these are the two things that you have to keep in mind. You have to balance these two things. So here are some examples. So I want you, at this point, to pause the video. And I actually want you to pause the video and see if you can figure out what goes in these spaces. Okay? So for this first one, okay, I know that I have to have conservation of mass. We'll do that first. So the mass numbers on the left have to equal the mass numbers on the right. So basically what this means is if I take 15 plus 17, that should equal whatever the mass number is of this thing plus 14. All right, and when I do that, I get x equals 18. So I know that this thing has a mass number of 18. Then I have to balance the charge. So that means that the sum of the atomic numbers on the left side have to be the same as the sum of the atomic numbers on the right side. So that means 8 plus 8 has to equal x, or here we'll do it as y plus 7. And in this case, y will equal 9. Okay, so I've got 18 over 9, and that means that this is an isotope of fluorine. Okay, so now you can try the other two if you got that one wrong, and I'll kind of work my way through these as well. For this next one, this is a 4 over 1, and when I look this up, this will be an isotope of hydrogen. Now, you can't really find this, but that's okay, all right? I'm just doing these as examples. So here, I have calcium reacting with something to make scandium plus a neutron. So this is a 1 over 1, and 1 over 1 would also be an isotope of hydrogen. All right, great. So let's talk about the types of nuclear decay, okay? And there are 4 types that I'm going to ask you to know for this class. All right, and the first one is alpha decay. Alpha decay is loss of an alpha particle. And an alpha particle is the nucleus of a helium isotope, where you have 2 protons and 2 neutrons. Okay, so for example, I could have 210, polonium 210, and that undergoes alpha decay. Okay, and I'm just going to indicate that this is alpha decay. And that's going to lose that alpha particle, that helium nucleus. Okay, now I have to figure out what's left. So I can do 210 equals 4 plus x. All right, and in that case, x is going to equal 206. And then I can also, so that means that my atomic number, mass number is going to be 206. And then from my atomic number, I know 84 equals 2 plus y. So y equals 82. So this is 82, and this is lead, okay? And if we think about it, all right, we have lost 2 protons and 2 neutrons, okay? That is alpha decay. So that's the first kind you're going to need to know. And when I say you need to know these, you need to be able to make a reaction like this, and you also need to know its effect on the chart of the nuclides, which I'll show you in a minute. The next one is beta decay or beta emission. And in beta decay or beta emission, what happens is a neutron turns into an electron plus a proton. So that is the symbol for a neutron. And that decomposes to an electron, which is that. Okay. For this class, we will oftentimes see them as beta particles. This is the Greek letter beta. Or you might also see them as electron plus a proton. Okay, so again, let's think about what's happening here. A neutron is being converted to a proton by releasing an electron, a beta particle. Okay, now these two both are in the nucleus, so they're really the ones that we care about. When we generate this beta particle, it now leaves the nucleus. Okay, so it's no longer in the nucleus. We don't care about it anymore. All right, so here, let's use this example. So this is molybdenum 96. And that undergoes beta decay, and it loses a beta particle. And when it does that, you'll notice that that does not affect the mass number. So the mass number is still 96, but the atomic number actually goes up by 1 because we have converted a neutron to a proton. Okay, so for example, this has 40, 56, sorry, 54 neutrons and 42 protons. Okay, and then this technetium has 53 neutrons and 43 protons. So we have converted a neutron to a proton. Okay, now numbers 3 and 4 I group because even though they are different reactions, they do the same net effect. Okay, so for both of these, what I'm taking is I'm taking a proton and I'm converting it to a neutron. So you'll notice it's just the opposite of beta decay, and the way it goes about it is a little different. So for example, positron emission makes a neutron, but it also makes a positron. And a positron is an antimatter particle of an electron, which means that it has all the same properties. It's just opposite in charge. So instead of having a negative charge, it has a positive charge. Okay, so this is a positron. Now, the other way that you could do this is with an electron capture, where you take that proton and what happens is a high energy electron goes into the nucleus and hits a proton. And when it does that, they merge and they form a neutron. So those are the things, the types of radioactive decay that you need to know. All right, so now how does this work? Well, I showed you this before, okay? Basically, you can take any isotope that is on this chart, and this chart tells you what isotope or what kind of decay that isotope does. So you just need to memorize this whole chart. How easy is that? I'm just kidding. You don't have to memorize that. I'm going to give it to you. Okay, and in fact, what I've done is I've taken it and I've broken it into a couple of different sections. Okay, and each of the sections we can find different kinds of radioactive decay. All right, so first things first, we're going to look at this isotope right here. Okay, now that isotope right there has, when I look at this, this x-axis is neutrons and the y-axis is protons. So this has 20 neutrons and 21 protons. So 20 neutrons plus 21 protons. Okay? And when I look at the chart, that is going to undergo electron capture. And if I go back up here, electron capture is when an electron hits a proton and makes a neutron. So we're going to end up losing a proton to make 20 protons, and I'm going to gain a neutron. All right, so now that's the kind of net effect of what's going on in number 1. All right, now 21 protons and 20 neutrons gives you a mass number of 41 and an atomic number of 21, which is scandium. And that is going to react with an electron because this is electron capture. And you could call this like E cap or something like that, just so I know what's going on. And that's going to make 41 over 20, calcium. Okay? Now, that's an example of how this works. So the other thing that you need to know on this is what effect these things have in the chart of the nuclides. So if I think about this, okay, what this means is that my number of protons goes down by 1, okay, which means that we move down. And my number of neutrons increases by 1, so we move to the right 1. So we go down and to the right 1. So we go, there's our starting location. Here, let me zoom in here. Okay, and we're going to move to this square right here. Now you'll notice that this square is not stable, and I'll show you what to do with that in a little while, okay? But for now, just make sure that you have this down, okay? So let's look at another example. Here's isotope number 2, okay? So why don't you pause and see if you can figure out what the reaction is that's going to occur with number 2, okay? See if you can write this kind of reaction for number 2. So with number 2, I have 10 neutrons plus 15 protons. All right, and so that gives me 25 over 15, and that is a phosphorus. Okay, and when I look at this, this is going to do a positron emission. Okay, so positron emission. And so maybe I'll even go the other way. So this is going to be a 0 plus 1 beta particle plus 14 and 25, and that will be silicon. Okay, so if I think about what's happening, my number of protons is going to go down, and my number of neutrons is going to go up. And that is the same exact effect that the electron capture had. So if I think about it, this also moves us down and to the right. Okay, so for these two, positron emission and electron capture, this is down 1 and right 1. Okay, or diagonal to the right 1. All right, so same thing for this third isotope down here that we're going to do. Okay, pause the video, see if you can write out the equation for this beta decay. So this isotope has 5 protons and 10 neutrons, which means it's 15 over 5. Oops, why did I put... (15 over 5), that's a boron. And that's going to undergo beta decay to a carbon. And that's how you write these equations out.